Okay, we'll get started. So let me start sharing.
Yep.
Okay, so last week we kind of started with trying to train a neural network, figuring out that just doing the LR find wasn't getting us any kind of a good training learning rate or a good training process. It tried to train, but then it would have this behavior where you would see the rise and fall. The mean was nowhere near 0. The standard deviation was nowhere near 1 for any of the layers. They kind of learned how to capture the activations using hooks and then plot the three things we desire. One is just the activation stats, which is the mean and the standard deviations, and then also subsequently the color plot of the histogram, which shows us the fraction of activations which are very low value compared to the total number of activations. This was a slight aside of how to claim memory, but sticking with initializations, the first thing we tried was the Xavier initialization, and we just did it not for a network, but to 50 or 100 matrix multiplication kind of indicated that one of the ways to improve it was by initializing to 1 by square root of the number of inputs. So since we have number of inputs of 100, the square root is 10, and 1 by 10 is 0.1. So that gives us, that begins to show us some number. But then we, excuse me, kind of learned about the definitions of variation, variance, mean, standard deviation, which is square root of variance, how to calculate it easily, learned about covariance, which was between two variables, X and Y, and then proceeded to kind of learn that even if we applied the Glorot initialization, we didn't manage to keep the mean and standard deviation close to where we wanted. So we then moved to a better initialization procedure called the timing initialization or Hay initialization. And that was a formula where you take square root of 2 by the number of inputs. So that's this formula here. And that began to give us a better initialization. And then we learned how to apply that to all our weights in the model. And then we kind of tried fitting with that. It was a little bit better. The mean you can see is a little closer to 0. Standard deviation still wasn't all that great. We realized, we weren't normalizing the inputs. So obviously, even if each of our layers as the input goes through is normalized, it doesn't help because the input is not normalized. So we took the time to normalize the input. There are two different ways to do it. You can do it through a batch transform callback so that each batch, if it is in training, applies this transform function. The other way to do it is, in the transform function, and then we plotted the graph, and it kind of turned out to be far better training. You can see that most of the layers, although by the time you get to the fourth layer, you see a little bit of degradation, but it's still far better than before. Means aren't perfectly 0. Standard deviation is not perfectly 1, but it's getting a lot better, and you see the depth charts are far better. The alternate method to do the norming is this way: apply it in the transform I function. And we said, wait, one of the ways that we can improve this is using a different ReLU than a standard ReLU. We called it a general ReLU, where we shift down if we need to, and then also apply a leakage and cap, which is a max value. In this case, we don't cap, but we shift it down, and we have a leaky on the negative side as well. We change the convolution definition to accept activation and hard-coded kind of the number of channels that we provide to these 1, 8, 16, 32, and 64. Otherwise, our convolutional network remains the same. Eventually, we flatten and then get the output. We apply or define the init weight functions, ran all that, and we saw that we got much better results. And then the depth charts or the plots and the mean, you can see the mean is much closer to 0. The standard deviation is much closer to 1. And the depth chart shows that very few of the activations are dead. So that's where we left it last time, and we'll proceed from here to look at one additional different initialization that sometimes gets applied, and then we look at the various norming functions. So there is this technique called layer-wise sequential unit variance. So one of the things that we saw is that as we go through the activation, and obviously we also saw that we could only apply for these kind of techniques, initialization and stuff, to the sequential layers. Here we are saying with layer-wise sequential unit variance, this technique can adjust to any activation in any neural network. So that's kind of what we're going to see. What we do here is we don't care about the way we initialize as much as what we do is we put a batch of data through the network, which we can do because we have very fine-grained control of the training process. So we can just push in a batch and then kill the fit function as we've seen and done before. And what we do is put a single batch, compute the mean of the output of the activation of a layer. And if the mean is not 0 and the variance is not 1, then we subtract a little bit from the mean and divide a little bit from the variance and redo the process. And we keep repeating the process until the output activation has 0 mean and 1 standard deviation. Right? So that's what we are trying to do. And we do that sequentially for every single layer in the network. So in this way, we don't care about initializing the weights, but what we do is we pass one batch and then make sure that the mean and the variation for every single layer sequentially is set to 0 and 1. Right? So let's see how we do that. We define a function called _LSUV stats, where we supply a hook, a model, and an input and an output, and then store them away. And then the LSUV init takes the model, the module, the input, and the single batch, grabs the hook, and while the standard deviation is not 1 and the mean is not 0, we do what I just described, which is that as long as the output of the model is not none, and the absolute value of the standard deviation from 1 is greater than 1 in neg3, or the absolute value of the mean is greater than 1 in neg3, that means that we want standard deviation to be 1 and the mean to be 0, with a delta allowed of only 1 in neg3. We subtract the current mean from the bias of the input, and we divide the weights, the data of the weights by the standard deviation, right? And we keep repeating this. So that's the function we define, and we grab the model and we grab the appropriate activations, which are the ReLUs and the cons, and we grab the ReLUs from the model's modules. We grab the convolutional layers from the model's modules as well. We zip those up. This is just a description of the model, and you can see that the ReLU and the cons are in groups, except for the last. And then check, this is just my stuff to understand what's in the MS, and MS would basically mean the ReLUs and the cons will get zipped, and we apply the LSUV in it which means this function gets applied to every layer. Every layer here means every combination of the value and the con, right? Because those two get treated as a single layer as it were. And then we train. Okay, and it'll train, and if you look at the plot, you'll see that those plots look as good as we had done with applying the behavior, applying the Kyming-Hay initialization. So this is yet another way. Here we don't care as much about initializing the weights because we pass a batch through the layers of the network and kind of standardize the network weight to be such that we get a mean of 0 and a standard deviation of 1. And you can see here that it's slightly less than 0 in this case for the mean, but not by much. And again, the standard deviations are pretty close to 1 as well. Now, that's kind of the variations in initialization. While you showed LSUV, but more often than not, as we move through the rest of the course, we'll be sticking with the Kyming-Hay initialization. The next things that people realize we could do better. So far, we've seen that we've just applied normalization, which means standard, subtract the mean and get the standard deviation to be 1 for the inputs. But there are better ways of norming that can be applied, and that's what we look at. So there was a paper called batch norm, and and that paper essentially pointed out that because we have very deep networks, that means multitude of layers, then this becomes training those deep neural networks becomes difficult because each layer's input changes during the training. Because even if we start with inputs which are 0 and 1, as we pass through multitude of layers, the output of those layers could potentially make the mean go away from 0 and the standard deviation go away from 1. And that in turn slows the learning rate down. And we already know that if we have a high learning rate, we get a good stable point that helps us adjust the weight so that the model generalizes a lot better. And so they call this phenomena where the mean and the variation keep shifting as we go through very deep networks as internal covariate shift. And they try to address it by normalizing the layer inputs, right? And the way they did it is to make the normalization a part of the model architecture and performing the normalization for each mini batch. But before we get into batch norm, which is a little bit more complicated than the other types of norm, let's look at what is a simpler technique, but along the same direction of norming. But in this case, we norm per layer, and that's called layer normalization. So let's look at again, there's a paper which describes this. You can go read that, but let's implement it ourselves, and then obviously we can switch and use PyTorch's implementation. So implementing it ourselves means defining these values. Basically, this EPS, the array value which is provided whenever we divide by something, and just in case that value is very small, close to 0 or whatever, we provide an EPS so that we add EPS to that 0-like value and ensure thereby that we are not dividing by 0. So we store that away, and then we define two parameters, a multiplication and an addition parameter. And we define them as parameters. So obviously we want to multiply by a value which is tensor 1 to start off with, and we add 0, or these are our initialized or initial values. And we are defining them as parameters so that they, meaning the network, can help us learn what these values should be. And then we define in the layer norm a forward function. Now, the thing to keep in mind is when we provide any input, such as, let's say, the MNIST passion, MNIST values, the typical parameter shape is NCHW for PyTorch and NHWC for TensorFlow. By that, what I mean is the first value in the shape is the number of elements in the batch, which is N. The second element is, or the second value in the shape is the number of channels or filters. And the third and the fourth are the height and the width of the image that we send in. So it's N, C, H, and W. Now, when we take the norm here for layer norm, and it's important to start paying attention to these details because subsequent norms will take norms across different axes. In this case, what we do is we take norm across all the channels, across all the, and across the height and the width of the image. So all channels, height, width. So the last three axes of the input that we provide. Therefore, the last three, given that there are 4, 0, 1, 2, 3, would be 1, 2, 3. So we mean the input X across 1, 2, 3, and we keep the dimensions. That's why we say keep them is true. What this means is each thing in the batch or each batch has its own normalization, right? And we find the mean and we find the variance. And what do? We subtract the mean that we have just found from X, and we divide by the variance. And since the variance could be very small, that's why we have the EPS value, and also take the square root. So we are actually dividing by the standard deviation. And then eventually when we return X, we use these two parameters. We multiply X by self.mult and we add this value of self.add. So that's what gets returned. So by doing this, what we're doing, one way to think about what is being done here and why this particular norming function seems to help us to learn much better than otherwise is to think of it this way, that what we are, obviously the network is deep and there are a lot of parameters that the network has to learn. But by providing this self.mult and self.add and at the same time kind of norming each layer, what we are trying to tell the network to do is, yes, you have all these different parameters, but you know what? Focus on this multiplication and addition parameters and try to make them such that that gives us really good results, right? And so that's kind of an intuitive way to think about it. So the learned parameters, which is self.mult and self.add, focus on those and adjust them to get where you want the distribution of the outputs to be mean 0 and a standard deviation of 1. So we provide the network with kind of an assist function of saying, here, use two more parameters, the add and the multiply, learn them, and I give you the ability to kind of manipulate them so that you give me a good mean close to 0 and a good standard deviation close to 1. So that's one way to think about what a layer norm function does. So we define that, and here we're just changing, just like we changed the convolutional definition before to accept an activation, we now change it to apply a norm. And depending on the norm, we may or may not bias, so we also begin to provide a bias. So this just says bias, make bias equal true in any layers that do not use norm. So that's what this does. If bias is none, then bias is not. If instance, no, if this line of code basically says if it's not a batch norm, then make the bias or apply bias. The layer definition is the same. The line of code we add is this bias line and the norm. Okay, so those are the two changes we make to the definition of convolutional. Get the model the same way as before. The important difference is we pass in the norm and apply it in the cases to each of our layers. And then we again try and train the model same as before and you'll see that it trains quickly and does so well as well. Okay, that's layer norm, but what's batch norm? So remember that in layer norm, we normed across all channels the height and width of the image. If instead we were to give or define a norm per channel, so that for if we had n number of channels, then we'd have n norms, then that is batch norm. Right? So essentially, we don't have in layer norm, for each layer, we just had a single norm, right? So we just had a single mult and a single add for each layer, regardless of the number of channels. Now what we're going to do is, depending on the number of channels, we'll have that many mults and that many adds for each of the channels. So we don't have just one add and one multiplier, but a bunch of them. And how many? One for every channel. So that's one important difference in batch norm. The second important difference is that during training, we are not just subtracting the mean and dividing by the standard deviation, but we do this lerp, and we have kind of seen what a lerp does, but we will look at it in greater granularity here. So what lerp does is, it's just a way to weight what we add and weigh multiple components going into a function. So if we were to average something, or let's even do for the average discussion, let's just take two values. Let's say there's a value of 5, a tensor of 5 and a tensor of 15. And we say that we are lerping with a tensor of 0.5. So what this means is, in this case, because it is 0.5, it will multiply 0.5 times the tensor 5 and 0.5 times the tensor 15 and add the two. So that is what it does. And obviously we'll calculate the result as tensor 10. But if suppose we were to choose the weight to be 0.75, what this means is it applies 0.75 to the second tensor here, which is 15, and 1 minus 0.75, which is 0.25. So you can see that it just applies the weight to one input and 1 minus the weight that we supply to the other input. So that's what a lerp function does. Right? So for example, if we just apply 1 to this, it means that it will apply 1 times 15, and then obviously 1 minus 1 to the other. So it will zero out this input. So we'll get the answer to be 15. So you can play with it to see, you know, how lerp actually works. Here's a different way of doing the same thing. You take one of the tensors, which is tensor 5, and then lerp tensor 15 and tensor 0.75. And that essentially means you apply 0.75 to 15 and then 0.25 to 5, and you add the two, and you'll see the same result as what we see up here. So that's what a lerp does, or the lerp function, if you will. Basically, it's an exponentially weighted moving average. That is, it weighs the two inputs depending on the weight that you provide. So remember that batch norm did two things. One, it created or for batch norm, we provide a ability to define a multiplier and an added for each channel. And we also do this lerping thing for in our execution. So let's again, just like layer norm, let's actually implement batch norm ourselves. And then obviously moving forward, we'll just use what PyTorch gives us. So how do we do batch norm implementation? Well, we take the NNF module, super init. This is the weight that we'll be providing to the lerping function. And we'll kind of learn which of and how it's applied. And then the EPS is very similar to what we saw before in the layer norm as well. So we store away two values, the momentum and the EPS, and then we define mults and adds. This is not just mult and add, it's not single, these are multiple values. And each of them is a parameter as we defined before. And like I keep saying, because there is one per each channel, we want the shape to be of the number of channels and then 1, 1, because the height and width dimensions are 1 and 1, or they're provided as 1 and 1 here as default. Then the self.adds is the same thing. And we initially start with the mean being, the mults being all 1 and the adds being all zeros, right? And then here we do something which, when we use the PyTorch version, we don't have to worry about, but currently we need to. What this register buffer does is it stores these values of the things called vars and means, which we'll be calculating in the model itself. Okay, and all this is handled by PyTorch behind or by itself, so we don't see it. But because we are trying to implement batchnom ourselves, we need to do this. So register buffer says save the vars and means as part of the model, right? And this is kind of where the part of the reason why implementing batchnom in multitude of complex networks, and there's been more debate recently as to whether or not applying batchnom is a good thing and whether we can get rid of batchnoms as we move towards more complicated and transformer networks and so on. But for now, batchnom definitely helps us for the type of networks that we are dealing with. What we are doing here is registering, if you will, which means that basically we are allowing the model to, or enabling the model to store the variance and the means that we calculate as part of the model, because we'll be using that in order to apply the norm. Okay, and then we define kind of the update stats function, which helps us take the mean. Now, notice how we take the mean. As I said before, we have 4 things, right? N, C, X, and W. Since in this case, we want the mean and the variance per channel, obviously the C will, the channels, which is the second parameter or the second of the shapes, will not be there, but we'll take the mean over the number of inputs in our, over the number of elements in the batch and the height and width. So we'll take it over 0 and then 2 and 3, and not over the channels, because we want one mean and one variance for each of the channels. So the mean is x.mean, and you can see the shapes we use for the mean are 0, 2, and 3. Same thing for the variance. And then here is where we use the lerping function, the details of which we saw before. We take the mean and we lerp it with a self.momentum. And when we do this, as we have seen before, what it means is that you apply 0.1 times the current value and 0.9 times the average, okay, that you have stored in the means up to this point. Those are the 2 inputs going into the lerp, okay? And we do the same thing of a lerp function on the variance as well, and we return the mean and the variance, which are the lerped version of the means and the variance. And then in the forward function, here's what we do. If we are in the training loop, then we run the update stats, which means we calculate the mean and the variance. Again, keep in mind that there will be mean and variance for each of the channels, right? Now, if we are not in the training loop, then we use the stored mean and variance to calculate. So in batchnom, what happens is we calculate the mean and variance per channel while training, and then we store them away. That's the reason why this registration is needed, because we are storing away the mean and the variance. And then during inference, we use the stored value of the mean and variance for each of the channels for each of the layers, right? And then we apply these mean and variance. So depending on whether we are in training or we are in inference, or I should say regardless of that, we subtract the mean, divide by the variance, and obviously we apply the EPS as well. And then return the self.mults. This is mults because there is multitude of the multiplication values, 1 per channel, and same thing for the self.adds. So this batchnom is, this is what the batchnom functionality is. And this is our own code for batch norm. Now
In
we
the
apply.
above, yes, update status function, update starts function. We have lerp, and lerp is applied on 2 arguments here. I was thinking maybe what's the difference between this and the 3 argument one, in which we have a full view of.
Oh, I think this just says lerp in place because there's lerp underscore. So it just lerps M and stores it in M.
Okay. So it's a different kind of in place function, right?
Yeah.
Okay. And so there's no need for a third argument here to tell it what's the ratio of the lerping here.
No, this is the ratio. Self.momentum is the ratio. But what we don't supply is the what we do not, the 2 inputs, because it says it kind of knows that I am lerping with my average and my current value. The current value is the value calculated for this particular mini batch, which is the current value of n. But it knows to take the second input from the average of n up to this point.
Okay, from the average of m.
Because self.means is this way of doing it is the third value is right here. This way of doing it basically says, okay, so that's why he showed us this variant. You see this variant?
Yes,
this variant is what is being done here. This guy is our self.means, which means the average. Okay. This guy is our m, which is the mini batch value of m that we are calculating on this mini batch. And the momentum is this value.
Okay.
You get that?
Yes.
Right? So if you look at this, self.mean is this tensor 5 equivalent.
Yeah, I was confused between that.
Yeah, that's our average value. So that's one input. M is the current mini batch. That's the second input. And we lerp the 2 using self.momentum. Right? But that?
Right. Yeah.
Okay. And then apply it and do all the rest of this bang stuff. But otherwise, same thing as before. And we can kind of increase the learning rate from 0.2 to 0.4 that you see here. Right? Now, we have learned kind of 2 different norms, right? So far, we have learned layer norm and batch norm and implemented it ourselves. Really quick, while that thing is running, I'd encourage you folks to also look at this paper. There we go. Can you see the PDF?
Yes, you can.
Okay. So this is a simple example of, I think, at least for me, this visualization really helps to solidify, and after not staring at it for a while, I forget, and I at least come back, and this is the way I can remember the norms. So there are 4 different variants of norms that are defined, and I kind of talked about it in words about we take it across channels, blah blah blah. This picture makes that very clear. The one thing to remember though is, because we can only kind of as humans interact easily with 3-dimensional pictures, they have flattened the height and width, combined them into kind of 1 dimension. So think of HW as a single dimension where height and width have been collapsed, right? So height and width is the vertical axis here. This axis is the number of channels, and then this is the number of inputs, if you will, in the batch. So N is the number of elements in the batch, C is the number of channels, and the height and width have been collapsed here. So what does batch norm do? Batch norm calculates the mean across the height and width, so across all of the height in this case is the height and width in this case is this axis, and across all the inputs in the batch. So remember, we did the batch norm across 0, 2, and 3. So 0 is N, 2 and 3 is HW. So that's why this blue chunk is what we're doing. And we get one set of mean and variance per channel. So this is if we have 1, 2, 3, 4, 5, 6 channels, we'll have 6 different values, right? Now, contrast batch norm with layer norm. Again, layer norm is a single value across all channels, but it's different norm for each of the elements in the batch. So therefore, you see what happens here is the direction or the norming is done across HW and across all the channels. So there isn't a value per channel, but there is a value for each of the elements in the batch. So that means we'll have this many, and the norming is done this way. There are 2 others which we haven't discussed, and sometimes group norm is used, and he talks about it. I haven't interacted or seen instance norm used in too many cases. Occasional papers do that. So these aren't as common as batch norm, but still good to know. An instance norm is just across an instance and one batch and one channel, right? So you can just see that it's just a single stack that we norm across. So it will be basically norming across 2 and 3 and not across 0 and 1, because 0 would be the number of inputs and 1 would be the channels. So we wouldn't do it across those 2. And group norm, instead of going all the way and getting all of the channels, in group norm, they say, I want to group certain specific channels, say half the channels or 2/3 of the, quarter of the channels, whatever. And if we do that, then we proceed somewhat, in this case, half the channels, so that we'll have not per channel, as in this example, but for half of the subset of the channels. So that is a grouping of the channels. And again, here we do the H and W, but we do it the mean over some portion of the channels. So this picture is really useful in mentally getting the image in your head of what is happening and across which axes of the shape do we norm when we do the different types of norming. Any questions? Okay, so the next set of steps that we take, given that we've studied these various different, initialization techniques, norming techniques and stuff, is step back and look at, okay, overall our goal initially, and the reason we kind of dived into all these details is because we were getting really crappy results when we started to try and get a good classification results. We were down in the dumps, like at 80% or 80, 70, high 70s, low 80s, mid 80s, so on. Now, the desired goal for us when we set out on this journey is to try and get the infrastructure set up. That means the fit function, the learner concept, as well as how to initialize the network, how to norm. And we'll also learn a few more things in this lecture, hopefully, that will get us to the goal of being competitive, meaning being among the state of the art in classifying the fashion MNIST data set. Now, when we are done classifying, we aren't done with because our overall goal is to head towards applying stable diffusion algorithms to the fashion MNIST data set, because it's a small data set and we can really learn the techniques and then expand or go bigger. But along the way, the first step would be to get a really good high classification score close to state of the art. Once we have done that, then we can take the next step of, oh, now let's also proceed towards stable diffusion and applying that. So that's what the towards 90% journey is. Now, here we take a batch size of 256, use number of workers 4, get the data loaders, and we are applying the batch norm. Because we have now coded the batch norm ourselves, we know what is in it, how it works, things like that. We just switch to using the patch norm of the PyTorch. Okay. And like I said before, even though we studied LSUV, as we move forward, we just use the apply IW, and the IW basically is the timing hair initialization. And we train, and we see it's important from now on to remember what score we get on the classification, which is running 3 epochs. While it now you can kind of begin to look at it, even here, the evaluation says we are at midpoint of the 80s, about 0.85. Let's just spend a minute or two to see where it gets us. And by doing this, we have applied we have applied the initialization, we have applied the batch norm, we have applied the general ReLU activation, and therefore, and the traditional callbacks that we have, such as the moving it on to the device, calculating the stats, things of that nature. And we are beginning to get reasonably good results and at reasonably good speed. We're at about 0.86 at this point, maybe around 0.88 when we are done. The one other thing which is typically done is as we get closer to the stable point that we are seeking, one of the things that's done is to lower the learning rate, because as we get closer to convergence or closer to where we would like to be and find the smooth part on our learning curve, we tend to reduce the learning rate a little bit, and we fine tune the model some more. Okay, and like I said, it's very close to 0.88. We ended up at 0.877. So the next step we do is we fine tune a little bit and do that for just a couple of epochs. And let's see where we end up as a result of that. We're getting very close to 0.9, whereas without initialization, without the norming function, without the improved ReLU, we were nowhere close to the 0.9 that we're getting to.
One thing I've observed is after training, the eval slightly lowers the accuracy. It should be increasing or it should be decreasing here. The eval in all the cases that we have come across.
Yeah, no, that's anticipated, right? Because the evaluation, remember, eval basically says it's the validation.
Yes,
you're
yes.
validating on the it's the validation data. So obviously your training loss would be much lower than your validation loss, because validation values are unseen values, right? So that's to be expected, correct?
Okay.
It would be lower than your, see, the loss is higher and the accuracy is lower, which is as expected. In fact, that is the reason. If you just do the evaluation on training, you're cheating, because you just, the network, you're just checking the network on things that it has seen before, and it will just do a really great job on that. But what you really want to test it on is things it hasn't seen before. And, I think, in fact, when I ran it before, I hit 0.9 just on the nose, but in this case, it's decided that it will still leave me a little bit short, but you can see that it's 0.899, which is pretty darn good. Now, this note, interestingly, for those of you who want to try this, I mean, I intend to do it, I just haven't had time to, there is a technique called, I forget this now, but it's basically stochastic weight averaging. So I wanted to kind of implement this stochastic weight averaging as a callback and see whether it improves it. And what stochastic weight averaging, just if you're interested, you can look up, there's a paper on it. And it's, I think, also implemented in PyTorch already. So you could even use the PyTorch version, but keeping with the spirit of the course, I wanted to implement it as a callback and then see whether I get the same result as what I would see if I were to use. And stochastic weight averaging basically does the following. Excuse me. it takes the weights. Here we are trained for two epochs, right? So once, let's say after this level of training, you get a particular set of weights for the model. And then once we take yet another step in the training, we get another set of weights. So as we'll see later, Jeremy himself also does manually what is equivalent to stochastic weight averaging. If you average the weights of this model and of this model and use the average weights of those two models to predict, you get a, more often than not, a better prediction than just using a model which uses the singular weights from further training. So you can implement that as a callback, and, and that's a note to myself saying, hey, maybe you want to try doing that as an exercise. And I would encourage people to try that if you're interested. Okay, so now we have done initialization, all the various kinds, norming, all the various kinds. We now move to learning about the optimizer. What are the various ways we can accelerate the optimization process and get a better network? And the other thing we'll do is also learn about schedulers, which in turn controls the optimizers and schedules the values that the optimizer uses. And that in turn also helps us get better results. And once we are done with that, then we'll move on to using better networks such as a ResNet instead of just a simple convolutional network that we've been using so far. So that is the next step in our journey. We just set up the all the initial steps are exactly the same as before. What we are now trying to do, as I said, is, okay, we have learned how to set up the learner, which is controlling the training process. We then learn to analyze the model itself and, realize that the model was in training very well. And that analysis helped us to figure out ways to initialize the model, ways to norm the model, and get our model to be training much better. Now we then turn our attention to yet another component of the whole training process, which is the optimizer, and try to see what can be done or what has been done with various techniques to improve the speed as well as the goodness of the network we get through changes in the optimizer. So far, we've been using kind of a standard stochastic gradient descent optimizer. Let's look at and what the code for that looks like, implement it ourselves, then we can start using the PyTorch version. Then we go on to implement improvements to the base stochastic gradient descent, a couple of improvements, combine them, apply yet another improvement called weight decay, and apply all of those improvements and see whether we can beat the 90% that we have barely touched in terms of the classification output. So all this we've seen before. These are all the callbacks that we defined. By now you should be familiar with metrics. There's a multi-class metrics, advanced stats, callbacks, which is device, metrics, progress. Define the new partial general value, subtract from 0.4, we don't apply the max. Apply the IW, which is init weights with a leak key of 0.1, and then a learning rate finder callback. So we apply a learning rate finder that we want to apply as well. This now is the code for what an optimizer would look like, the standard no-frills stochastic gradient optimizer. Obviously, we'll implement it ourselves in code and then switch to using the PyTorch once we know that this works. So what does an optimizer do? Let's look at it. Basically, it takes parameters, it takes a learning rate, and it takes a weight decay. So the input to an optimizer are the parameters of each of the layers, a learning rate, and weight decay. Since the params function of a module in PyTorch is a generator, so it just it lazily evaluates the parameters. So in order to for us to deal with it easier, we list it so that we have a list of all of the parameters. Then we just use the fast core store attr to store the learning rate and weight decay. The one other thing that we store is the batch number, and we need this because you'll see that it's needed for applying the norm or doing something. We need this, so we create an index and initialize it at 0. The optimizer, as we have seen, we step it, and we'll also learn what optimization step. We've already seen that, but we will now see another step that we take called a regularization step, and we'll learn more about that as we go through the rest of the notebook. So here, with torch.nograd, which means you don't want to take yet another gradient. The other way to do it is if we say p.data, that will actually touch the actual stored data without the gradients attached to it. So that's yet another way if we want to not use torch.nograd. But here we say with torch.nograd, for every parameter in the parameters, you take a regularization step of the parameter and you take an optimization step of the parameter. Now, what this does, we'll look at in detail, and then we increment the step, right, which is the batch number. So we increment that once we have taken the optimization and regularization steps for the parameter. So what is the optimization step? It's basically what we have done before. We take the parameter and then take the gradient of the parameter and then multiply it by some factor called the learning rate, and we subtract it from the parameters. That's the optimization step. The regularization step is something that's new. So this is where we apply this technique called weight decay, which we'll discuss in more detail just in a few minutes. But in an equation sense, if the weight decay is not 0 and instead there is a weight decay value given to you, then here is the formula that you apply. And basically, conceptually, what it does is think of it as weight decay is yet another, there are two different ways to regularize. One is called L2 regularization, the other is weight decay. Both of them, what they try to do is prevent weights from getting so large that it prevents the model from generalizing well. So it kind of applies a penalty or tries to say learn well by using small values for weights, so that any weight value which becomes very large, it tends to penalize that. And so it tends to kind of hamper the growth of the weights, is the way at least I intuitively think about it. And the way it does that is by multiplying the learning rate times whatever the value weight decay is, and it subtracts from 1 and multiplies the weights. So because this value reduces the parameters weights, right? So that's what happens in the regularization step. And of course, we have always seen the zero grad, which is if you apply the p.grad.data and in place zeroing of that. So that is the set of functions that a baseline stochastic gradient descent optimizer should do. It should regularize, it should be able to step, it should be able to zero out the gradients, right? And the step does two things, the optimization step and the regularization step. Okay, so we now use the model as before, and the optimization function that we provide to it is our own stochastic gradient code, STD, which we have just coded. Okay, and we apply that. And we train.
What was the WD here? The
weight decay value.
Okay, weight decay. Yeah.
That's the weight decay. Right. So we trained. So here's the discussion. And in fact, if you want, there are much good explanations of weight decay that you can go look up on the web and learn about what weight decay actually does and why it's useful, right? And how it helps us get to what we are kind of aiming towards. I won't spend too much of my time explaining it, but just a little bit here. As I said, it's easier to dive into explanatory things from Medium or other pores. But bottom line, what happens is that one technique to reduce the weights is to do something called L2 regularization. So what is L2 regularization? It means that adding the square of the weights to the loss function. That means you determine what a set of weights are, compute the square of all of the weights, and then add that to the loss. Now, how does that help? It helps because the loss function, remember, is a penalizing function. You want to reduce the loss function. If you add the square of the weights to it, that means if the weights are big, the loss function will be big. So that means since we want to reduce it, the network will perform better if the weights are actually smaller. So the network will be motivated to find a smaller set of weights, or will be forced to find a smaller set of weights, and small set of weights distributed across all the weights helps us to generalize better. So here L is loss plus the sum of weight times the power 2. That means square of the weights. Now, what we care about is the derivative of the above equation. So that means, weight squared. So when we derive this, then it's the derivative of the loss with respect to the weights. And so it will become 2 times the weight. But 2 times the weight, 2 is just a constant. So it will be the sum of 2 times the weight. But because 2 is just a constant, we can kind of include it into the equation itself. So it just then says if you want to reduce this value, just multiply it, just like we reduce the learning rate by whatever the LR value is. So we apply a similar kind of concept and say weight decay. So it's a fraction. So you apply the fraction to the weight, right? And then that becomes the gradient of the weight will be the weight decay, which is a fraction times the weight, just like the learning rate becomes self.LR times the gradient. And now this says we are applying some kind of decay to the weight and making it the weight gradient. But now eventually the weight gradient is added back to the weight. So in that sense, all that can be done is we could combine all of these and just say eventually that the parameter just needs to be reduced by the product of the learning rate and the weight decay. So as long as P is reduced by the product of 1 minus the learning rate times weight decay, that's what we do, and that is the weight decay equation. And as I said, you can kind of work through and push through the math by going through many of the pores offline. But the concept of weight decay conceptually to remember is it tries to keep the weights low in order to help the network to generalize better. Okay, so that's kind of what we have done here. Of course, in this case, I think, if I'm not mistaken, we apply a weight decay of 0 with our base stochastic gradient descent. This just explains the concept. Now, the next 2 things we'll do is improve the base stochastic gradient descent by applying 2 different concepts which help us improve the optimization process and get us to a faster convergence as well as a better model trained through this faster converging process. The first concept we use in this is called momentum. And here's where the LERP function that we had learned before will yet again come in handy. So what is momentum? Let's say we define x's as this function touch a linear value between -4 and 4, and we take 100 points. And the y's are just a particular function that's defined like this. All these blue dots are the y's, okay? And the x's are from -4 to 4, and we have chosen 100 different points where the y function based on the x is defined by the second equation, and the x's are defined by the first equation. And then we just plot the x's and the y's. Right, so now let's try to understand what happens if we provide different levels of what we'll call beta, or which is a proxy for momentum, and what happens when we provide different values for beta and we try to learn to track the y's, which is kind of what we want to do, right? Is predict the y, which is the dependent variable. Now, when beta is 0.5, you can see that the curve, the red curve, which is the plot of the y, or for what we're trying to predict, tracks almost every single fluctuation in the values. So as our y values change in swing from point to point, you can see that this curve traces every single point almost, and you can see the waviness and non-smoothness, as it were, of this curve. As you increase beta of 0.7, so what that means is you give more weight to the average value that you're predicting than to the instantaneous value obtained from any one of these points. That means that if this group of points begins to go downwards here, because you're weighting the average a little bit more, you will see the downward trend a little later than instantaneously. In this case, you're seeing the change and reacting to every single value of y as it changes. You're reacting to it moment by moment. If this y were to go up, your graph will go up. If the y were to come down, it will come down immediately. So that's why this is tracking all these points well, but it's extraordinarily curvy. Here, you can see the curve begin to smooth out and not react to every single up and down movement or sideways movement of these points as you increase the beta, right? So you can see that this curve is much smoother than this one. But there is an issue, right? It does not change as fast as this curve does as the data changes. And if we were to increase beta even more, you can see the effect increase dramatically. So you can see that even though these points have begun to increase substantially, for the curve to change direction, it takes longer than in these two cases. So as the beta is increased, what we are doing is providing more emphasis on the average. And the average is determined by the past, not the current value. And the past value continues to push this red curve to change slower, even though these values. So you see, for the red curve to begin to slope down, you need a substantial number of these blue points to be lower than their earlier values before the red curve changes and moves down. So what this essentially does is, as we change beta and as we increase the beta value, it tends to shift the weighting, the LERP weighting, towards the average and less towards the instantaneous value. Now that's a desirable behavior because it gives us a smoother curve, but there's a limit. If we do it too much, then we'll have a curve which is very smooth. This curve is obviously tremendously smoother than this, but it's nowhere near the shape of this curve. Why? Because it's heavily weighting the average. So by the time it begins to show a downward slope, it needs all of the data in this place here before it begins to downward slope. Right? But these charts, what they are useful is to understand what lerping does, what momentum does, and so that we can retain these pictures in our head as we change the value of momentum. Basically, momentum helps us. It says if you're changing in a particular direction and you want to apply, it lerps towards the average and away from the instantaneous value changes, right? But there are, as we've seen, we want to keep it reasonable and not go overboard, for then it will completely stop tracking. It will be a very smooth curve, but it will nowhere be close to what we're predicting. So now with that concept in mind of what beta or momentum does, let's actually look at the implementation of momentum as it applies to stochastic gradient descent. Right. So now we define a momentum inherit from stochastic gradient descent, the same inputs as before, but we take in a new value called momentum and we store that away. In the optimization step, So what do we do now to use the momentum? Okay, so what we do is we check whether there is a gradient average, and if it's not, create a gradient average of zeros and make it the same shape as the gradient of the parameters, and then use the lerp function. So the new gradient average is the gradient average times the momentum, and the gradient average that's calculated sorry, let me repeat. The stored gradient average will be the gradient average times the momentum. So this is the average, and this is the instantaneous value, which will be multiplied by 1 minus self-taught momentum. So if momentum is 0.9, that means we are weighing the average to be 0.9, and we are weighting the instantaneous value of the gradient to be 0.1. So it will be much more like that shape rather than like this, right? Because we are weighting the gradient average higher. And then we apply the same self-taught learning rate times the gradient average. Okay, so that's our own definition of momentum. And then using this momentum allows us to now jack up the learning rate. Until now, if you saw, we were using 0.2 or 0.4. We are now able to apply to the same network a learning rate of 1.5. Any questions on the implementation of momentum? Okay, and then we check the results. Of course, we can also see it. How many? We do it for 3 epochs. So while it's training, and we got it. The next thing, and momentum was actually a technique that I think people developed and wrote a paper about and stuff. There's a second technique which interestingly came about and is widely applied, but it was actually first, there wasn't any paper or anything written about it. It was just discussed in a Coursera course and has become a standard that's applied. Kind of funny how something taught in a course has become so standardized. But anyway, look at the results of applying momentum as part of the optimizer. These look really good with respect to our desired behavior. The second technique we apply to optimization besides momentum is called RMS prop. And what RMS prop does is similar to momentum, but instead of using the weighted average or lerping of the gradient, what we do is we use a lerping of the square of the gradient. Okay, and so think of it, at least in my mind, again, I think of it as kind of, when we did this norming and stuff, we applied mean and a variance. So in this case, momentum is kind of what is done to the mean. We can think of it that way, that we kind of lerp the moving average of the gradient, but then we also want to lerp the square of the gradients and utilize that as well. And that's what RMS prop does. But in this case, the idea is that the large gradient square, right, which means that if you're lerping square of the gradient, and if the square of the gradients is large, that means the variation is very high. And if the variation is high, then you don't want to update that, or your updates should be small, because if the variance is very high, the particular direction that you're going to be moving in is not very confident, or you can't be very confident when there is so much variation from point to point in the direction. So when your gradient is very high, then you do not want the update to be significant. So you want to divide the update, right? So that's what we do here. That is, so when a large gradient square indicates a large variance of the gradient, so we divide the gradient by the square root of the square of the average with an EPS added on, right? So conceptually, what we are doing is we are saying if the variance, so again, think of it in terms of this diagram, or at least I tend to. So if the update you're doing is very, or if the variance that you're getting at point to point as you move along is very high, you do not want the updates to your Y to be very high because you're uncertain of the direction in which, because these points are moving in all different directions. So you want to divide the gradient at that point by the lerped value of the square of the gradient to keep the update small. If on the other hand, your variance is not high, which means all the points are moving in a similar direction, you want to allow a large update because then you can be reasonably confident that the direction you're moving in is correct. So you allow a large update. So not only do you apply momentum, but you also apply this RMS prop where you divide by the square of the gradient. If the variance is high, you lower the update. If the variance is low, you allow for a larger update. That's the conceptual thing about RMS prop. And for that, we use the square of the gradient and apply the lerping to the square of the gradients. Right? So that's what this is. When we do not have much variation, we do a large update. While if the variance is high, we do a small update. And we ensure that by dividing by the square of the values. Right? So this is RMS prop, store away square momentum. He just calls it square momentum. It, in fact, when we apply the combination of both, it will be called beta 2. Remember that we also call momentum beta. So it's called beta 1 and beta 2 eventually when we start combining RMS prop and momentum. But let's just refer to it as square momentum here. Store it away, and in the optimization step, do the same thing of if you don't have an attribute, and then the square average. So we take the square average multiplied by the square momentum, and then we take the instantaneous gradient, square it, and apply the 1 minus the self-dot square momentum. And then we do the same thing. We apply the learning rate, p dot grad, and then we divide by this. But then again, remember that it's always important whenever we are dividing by something to ensure a division by 0 doesn't happen. So we add the self-dot EPS. Any questions on this RMS prop? By the way, just as an aside, let's take a look. We are at about 87.4. We were, I think, at 899 previously, if I recall correctly. Now let's do this bit with just RMS prop, and we plot that. And what he says here, interestingly, is that you could typically with the standard optimizers that I use these days, it's Adam or Adam W, which are both variations of the concept is the same. You apply both momentum and RMS prop. But it is possible to just use one or the other as part of the optimizer and leave out the other. And he points out that EfficientNet is an architecture that's often trained with just RMS prop. RMS prop and momentum together is not Adam. And what we provided as momentum and as square momentum are referred to in Adam parlance as beta 1 and beta 2. Right? And you can see we are at a little bit even lower, 0.854, 0.874. We were at about 0.899 before. Now we apply Adam, and Adam is the combination of momentum and RMS prop, so beta 1 and beta 2, as I said, learning rate, weight decay, store away all the values. Let's look at what we do when the optimization step happens. So if it doesn't have these attributes, and in our own code, to keep things simple, we are storing the average, the square average, and so on as attributes of the parameters. As we'll see shortly, that's not the way PyTorch does it. That's the way we have done it in our own code in order to keep things simple. But when we switch to using PyTorch, there'll be a little bit of adjustment because PyTorch uses dictionaries to store the values of the parameters. So we'll have to adjust a few things in order to kind of use the PyTorch way of using the optimizer. But here we just say, okay, if you have an average or if it doesn't have an average or a square average parameter, let's just define those, establish those, and then the average is self.beta 1 times the average and 1 minus self.beta 1 times the gradient. The instantaneous gradient is 1 minus self.beta, and the average is the self.beta, which means we're applying the momentum. We are doing the lerping, the momentum lerping, if you will, right? And then we do something here. Thankfully, we don't have to worry about all these details eventually when we switch to the PyTorch version, but it is important to know what is actually going on. So here, the problem with the square of the gradient would be, obviously calculating the average. It doesn't matter because we just start with an average of 0. But what do we do when we have to use the square of the average? And that will again be 0. So what we do is we unbias. And in this case, in order to keep the value simple, he just says that the way that he's going to unbias the average is by dividing by the self.data1, which is the momentum, and using and this is the reason that we had, if you recall, we had in std stored away the batch index as self.I. And this is the place where that comes in handy. We just raise the data 1 to the power of self.I plus 1. So instead of 0, we make it 1. So the first example, if we know that we should be closer by, and you can work through and push through the math by doing the math by hand, but think of it this way, that it's just an adjustment that is necessary in order to get the values closer to what we want it to be. And so we unbias the average by a particular amount, depending on which of the, where we are in the batches. That's why we use the index. And then the square average is the same. We just have lerped the square of the average, and we unbias the square of the average as well. And then the last thing we do is jointly apply the learning rate times the unbiased average, and then the unbiased square average, and add the self.EPS and take the square root. So that becomes the combination of momentum and the RMS prop. So that's the definition of Adam. Then we apply Adam, is application of both of these. And we are, together we get past 90% this time around. Okay, while it's training, let's talk a little bit about the changes that we will need to make in interacting with the PyTorch optimizer. So scheduler, we have already seen with a learning rate callback that we can change or adjust the learning rate as we move through the training, right? But there are ways by which the learning rate can be adjusted, which are much better and where PyTorch provides us the control rather than us having to do it ourselves. Now, this is one instance where he says, okay, I'm not going to stick with the rule that we have followed in this course throughout, which is implement everything ourselves and only then switch to using the PyTorch version. There's nothing inherently new that we will learn, unlike in case of Adam and other things that we implemented and we learned how those things work. The schedulers are kind of obvious in what they do. They just control the value, the changes in the values. So I'm just going to adopt or use the PyTorch schedulers directly. And by the way, we haven't yet gotten to the 889 or 899. We're about at 0.871. But again, keep in mind that this is just 3 epochs. If we did 5 or 6 epochs, maybe we may get to 0.9. But let's keep going. So what we say is that we will begin to use schedulers. So the schedulers, because they need to change the values that are there in the parameters, that are there in the optimizers, will need the optimizers provided as input to the scheduler, because the scheduler changes values that are within the optimizer that the optimizer uses, such as the learning rate, right? So, and here, but if we actually do this, we can kind of it shows you all of the different types of schedulers that are available in the learning rate scheduler. There can be a change scheduler, there is a constant learning rate, there's a cosine annealing rate, there is a cosine annealing warm restarts, there's an exponential learning rate, there's an LR scheduler, multiplicative, blah, 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 blah. So this is one way to find out what are all there. The other way to do it is to actually find out, you do a dir on an LR scheduler, and as we did this here, we saw that actually here, and so you see this, the ones that we seem to want are ones which have the first letter to be capital and the second letter to be a small letter, right? Uncapitalized. The first letter is capitalized, the second is not. So using that, what he does is he says, I want a directory of LR scheduler where the first letter is capitalized and the second letter is lower. So let's just, and he finds out, what are all the different types of schedulers that we have. And then this is just yet another way of doing the same thing using a filter function. But now this is where what I said earlier of the API for a PyTorch optimizer is different than what we have implemented. We stored the values in the attributes like the average and the square average and stuff. That's not what PyTorch does. So let's learn a little bit about how the interface for a PyTorch optimizer is. So PyTorch schedulers work with PyTorch optimizers, right? They have a different API. So we create, in order to understand the API, we create a simple learner and pass in a single batch callback, right? We know that what it does is you pass a single batch and then kill the set. So that's what we do. And so we store the optimizer from the learner into opt. And then we say, we try to find out what is in the optimizer, right? Because we join O for O in the directory of optimizer. And, we don't want to touch private things. So we say if O of 0 not equal to underscore. So it means it doesn't start with an underscore. And you see all these different values are there in the optimizer. Right? And if you just, this is me figuring out what is in the optimizer. Now remember that our default optimizer that we provide to a learner is the stochastic gradient descent, is the torch.optim.std.std. And what that has is all these values, a parameter group with a value, it's actually a dictionary. And it is parameter group 0, dampening 0, different table, blah, 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 whatever these different values. Now, what are the parameter groups? So parameter groups are groups of parameters, okay? And in our current thing that we're doing, we just have a single parameter group. That means all our parameters are stored in one group. Now, why is there this concept of parameter groups, and why could there be multiple parameter groups in a network? That is something that is very handy when we apply transfer learning or when we want to apply different learning rates to different groups of our layers. So if we want to apply, typically in a deep network, there are things which are called head, for example, where we flatten the network in our own convolutional network. That could be considered the head, and we will want to apply a different learning rate to that head or that layer of the network, and a different learning rate to other layers of the network. And in such instances, these layers would have different, they would be different parameter groups. Currently, we don't care about that. So we just have a single parameter group. Okay? And also as before, since model.parameters is a generator, we create the parameters from it by listing it. And then we can check the state of the optimizer. The state of the optimizer is a dictionary with the keys as the parameter tensors. So think of this, you have to remember that, or it's kind of interesting that the state of the parameter is a dictionary with the parameters which are tensors as indices. It's kind of interesting because there are numerical indices in this case, because the parameters are obviously numerical values, they are tensors, right? So the tensors are keys and the values are the various values corresponding to the parameters. So for example, the learning rate would be value, the average values that we compute could be a value, things of this nature. So in our code, we stored these as attributes, right? P.average, P.square.average, where P is the parameter. PyTorch, on the other hand, does it differently. It has a dictionary, and you use the parameter to index into the dictionary. And the parameter is a tensor. You use the tensor as a key, and the value is the state. So, for example, ST has a momentum buffer. Now, because we have not done any training, the momentum buffer is a 0 value, right? So, if we do parameters, as I said, this learn.model.parameters is a generator, converted iterator. Next, we get the parameter, and then we figure out the state using the parameter as an index and call that the state. If we hit param, then it gives you the parameter as an example. Now you can try, I won't do it here, but you can try op.state, uncomment it, and see what is in it. It will give you all, and it's like a long printout, which I'm not going to do. Then state says momentum buffer, and as explained before, right now we haven't done anything with momentum, so it shows none. What is the length of our parameter groups? That's single parameter group, as I've been saying, and each parameter group is a dictionary. Right? So op.param groups 0, which is the single parameter group that we have. Let's say PG, and let's call it a parameter group. And you can see that the type of parameter group is the dictionary. And if you want to know the keys of the parameter groups, then you can just list it, and a listing of a dictionary gives all the keys. So these are all the keys. And the key says this is the parameters, the learning rate, the momentum, the weight decay. Nesterov is yet another value in different variation of optimization, optimizer, and so on, right? Now, what do we do when we want to create a cosine annealing scheduler? So what we mean by a cosine annealing scheduler is we want the learning rate of the optimizer to change in the shape of a cosine function as we proceed through training, right? So using a PyTorch optimizer, what we do is we choose an LR scheduler dot cosine annealing learning rate, right? So that's the scheduler that we want to use. As I said before, a scheduler controls the variations of parameters within the optimizer. So we need to provide the scheduler with the optimizer. We provide that. And the other thing we provide is we also tell it to say for how many steps. So that's the other thing we provide to the scheduler. So we provide two things. One is the optimizer, and the other is the max number of steps. Right? So that's what is explained here. And I already talked a little bit about this, that the reason to change the learning rate by parameter groups is because we could want to change different layers of our network, change the learning rate for different layers of the network in different ways. And that's the reason we have these things called parameter groups, because you can group the layers and change the learning rate of the group layers in different ways. So we define that, kind of just poking to see what is there. And one of the things that's there is the Tmax. The other things that are there are something called the base LRs, which is the learning rate that you start from, right? So when we set the learning rate to pass it into our learner, the learning rate that we set eventually goes to the optimizer as the base learning rate. So the learning rate that we pass in, the 0.2, the 0.4, the 1.5 and stuff, is passed into the optimizer, and it starts as the base learning rate. But the scheduler can begin to change that value. Right? In our case, it will be a list, because one for each parameter group. Of course, for us, it's just a single value. because there is only one parameter group. But you can see that scheduler has all of these different kinds of values in it. And you can find what is the base learning rate, 0.06. You can also get the most recent learning rate, which, because we haven't changed it, is the get last learning rate function. You can see that that function or method is right there. Right? And he just says, okay, I couldn't find in PyTorch a way by which I can look at how my scheduler changes the learning rate. So he defined his own function, which is you pass in the scheduler, you pass in the number of steps, which in our case that we did here is 100, store away the learning rates in scheduler.getLastLearningRate, and then for I in the range of steps, which means for 100 steps, you step the optimizer, step the scheduler, update the learning rate list by the last learning rate, and then plot it. So you're just getting a plot of how the scheduler is changing our learning rate, right? And in this case, he just is plotting the learning rates using this function for our scheduler, which we defined here, which is our cosine annealing scheduler, which has an optimizer. And our optimizer, I believe, is an Adam optimizer now, and for 100 steps. And he does it for a little more than 100 steps to show that because it is following a cosine graph, it will begin to turn up again, right? So if we do that, we begin to see that the learning rate is changed in accordance with a cosine graph, right? So that's what a scheduler helps us to do. It helps us to change values within the optimizer, typically the learning rate, but also other values, following what we specify it to be, right? So, and this is just a comment, and this is something that I think I particularly like about Jupyter Notebook environment and stuff is you can really play with each of these elements, figure out what they are, look into the details. That's the advantage of working in a notebook-like environment as you're experimenting, because you can really investigate every little thing and try to understand what's going on. Now he defines a scheduler callbacks in order to be able to control the schedule, control the scheduler as part of our training process. And he just defines a base schedule callback, right, which is defined as a scheduler. And then before you fit, you pass the optimizer that you define in the learner and pass it to the scheduler. And then the scheduler just steps, right, as we know that that's what happens. And then if you want to do a batch schedule, this is a basic scheduler. You can do a batch scheduler, which is after a batch, then you do a self.step and you pass in the learner, right? This one we will not worry about right now because I think this got fixed where the new callback that he is now defining is called a recorder callback. And the recorder callback is something that you define to keep track of all the different things that are going on in our learner, right? And these are things like learning rate, momentum, square momentum, things of this nature. So, and the way we do it is to define a dictionary, pass in the name of the parameter that we want to track. We will use the example of the learning rate and then define a function to track that value. So the function that we'll be using is called _LR, which it is going to grab from the callback and then look up its param groups property and grab the learning rate, right? And then, so what the recorder callback does is you pass it a dictionary. This dictionary is what will tell the recorder to, or we will tell a recorder which values it needs to record, okay? And the records are K, which is the key and the list of values for each key in the dictionary. So if there are multiple values that you want to track, each value will have a list of values corresponding to each key will have a list of values corresponding to it. And then the TG is just the parameter groups. In our case, we'll just have a single parameter group. And what we do after the batch is run, if we are not in training, and we are not, obviously the tracking is done during training, not during inference. So if we are not in training, we just return, we don't do anything. But if we are in training, then for each key and value in the dictionary, we add to the self.rex, which is the dictionary itself, for the appropriate key, because the value is a list, append the value, right? And then also add a plot function so we can look at what we are recording. So that's a recorder callback. And we define the learning rate, provide it a basic callback, and essentially all it does is it captures for the current callback for the parameter groups the value of the learning rate. Right now, as we have seen, the scheduler requires that we provide the max number of steps that the scheduler has to take. Right now, the max number of steps that the scheduler has to take, if we think of it in terms of the number of batches in the train, then we can calculate that using the length of DLS train, right? That tells you how many batches are there in the length in the training data, and we multiply it by the number of epochs. So if we have, for example, 3 epochs and DLS train is 59, then 3 times 59 will be Tmax, right? If we do for each batch, the Tmax is 3 times however many batches we have in a training data loader, right? Because we are doing 3 epochs and there are 59 mini batches, right? So we define Tmax to be 3 times the length of the DLS train. We define a scheduler to be LR scheduler cosine annealing learning rate, and we provide the Tmax to be 3 times what we have defined already. We just pass in the Tmax to be the Tmax that we have determined, define the callbacks that we already had defined, run this, and track the recorder callback. And here's where you begin to also see the advantage of providing the extra callback, right, which is only provided to the fit function and removed. If you go back and look at the code for the learner, this extra callbacks get added. So extra is the batch scheduler callback with the scheduler and the record. So this gets added as callbacks just to the overall set of callbacks we use and get used in the fit function. Right, so we are getting very close to where we were before, which is 0.899 at 0.882. And this is obviously the plot of our training, but we can now plot the recorder, which gives us, here is where we used the plot function from the recorder. That's the function we're using to plot this. And we can see that the learning rate is being changed by this callback through the scheduler, through the optimizer to what we want it to be. Now, what we have done previously is a batch. So we change the learning rate for every time we use a new mini batch. That's why we said 3 times 59 is the max number of steps, right? So we change the learning rate according to the cosine curve at every mini batch. So for every mini batch, we used a slightly different value of the learning rate. Instead, what we could do is use the same learning rate for the entire epoch. That means all the mini batch, all 59 mini batches will run through with the same learning rate. Then we'll change the learning rate and do it again. Then we'll change the learning rate yet again for the same epoch and do it again. That is different than what we have done here, because in that case, when we just change the learning rate per epoch, it will still do it kind of consistent with the shape of the cosine curve, but it will only choose 3 points from the cosine curve. Whereas, we would have done it like following this smooth curve when we had this 3 times 59 point. So we define an epoch scheduler callback, which after epoch steps the learner, right? So here the stepping is done after each epoch instead of after each mini batch. Now we need to change the Tmax, and the Tmax is 3 because we only change it after each epoch, not after every mini batch, right? If we were changing it after every mini batch, then it's 3 times the length of dls.train. But since here we are changing it only after every epoch, it's just 3. So we done that, and we see what the output is, and we'll also, you can already see what I mentioned before, that there are only 3 changes or 3 steps of the LR. Those curves. The one particular thing which is in fact baked into FastAI and something that Demi uses a lot is to adhere to what is referred to as one-cycle training. And the paper is there. This paper was authored by Leslie Smith. I don't know if it was published, but it's there on arXiv that you can read. And that is something that provides us with even better change in the learning rate modulations. And you can see we're getting even closer and closer to the 0.899 or so that we were getting. And again, all with just 3 epochs. And you can see the change has only happened. First epoch, the value is this. Second epoch, the learning rate value is this. Third epoch, the learning rate value is that. We gradually reduce it as we go from being consistent with somewhat of a cosine curve. The single learning rate is something that corresponds to the paper authored by Leslie Smith. And here he defines beta 1 and beta 2 and begins to capture, besides the learning rate, also let's look at beta 1. And beta 1 essentially captures from the parameter group the betas 0. Remember that the reason for, or our Adam stores the values for momentum and the square of momentum as betas, and beta 0 is the momentum value. And if you want, for example, to play with also doing the square, then you would add like square momentum or something and put it as underscore beta 2 and define underscore beta 2 callback as CBPG betas 1. Okay, that would be an interesting experiment to play with so that you can become familiar with how to modulate or more how to change these things. The rest of the things is exactly the same. Notice that we have increased the learning rate to be 6 ENEC 2. We do 5 epochs now instead of the 3 epochs we were doing earlier. And we apply all the other things similar to what we used to do before. And what is one cycle doing, right, as compared to what we were trying to do earlier? So what one cycle training does is it starts the learning rate very low and then increases the learning rate to be high and then slowly brings the learning rate down again. And on the other hand, we'll see that correspondingly, what it does is it starts momentum to be very high, then decreases the momentum, and then increases it again. So it's almost, in a way, mirror image of what is done with the learning rate. It starts learning rate slow, goes up to a high learning rate, and then brings it down again. In case of momentum, starts it high, goes down, and then brings it up again. Now, why is that, or what's the rationale or thinking behind that? The thinking behind that is as follows. We start the learning rate low because we do not have a very good or a perfectly initialized model. As we've seen before, initialization is fairly important. Despite all our different methods, we are kind of still imperfect in it. So start the learning rate slow because we do not have a model values or weight parameters which are very well initialized. And then as we use complicated models, that is even more the case, right? So the low learning rate ensures that we do not go off track initially when the weights or the parameters are not very stable and they don't make a whole lot of sense. Then as we push multiple batches of data into the network, we kind of begin to allow the learning rate to increase, right? Because we are now a little more confident after we have learned a little bit that we are in a better space in terms of optimization. Now, and during this time, that means after the initial phase, if the values of our movement in weights is in the same direction, then we let the momentum be high, which means that we are giving a significant weight to the average. So if in the initial phases, when we are uncertain, but we find certainty by moving in the same direction, then we say go faster because it seems we can trust the direction we are moving in. That's why momentum is high initially, as opposed to learning rate being low initially. But if in the early stages, things are moving in a very different direction, then we say, no, slow it down. And that's kind of the reason for the value of the momentum in the beginning. Then we get to the good part of the high weight space. There we have a high learning rate. And when we have that, then we don't need as much high momentum. And as we get to the optimal, then we generally want a low learning rate, as you've seen. And we are back to using a higher momentum because we are more confident. So that's, and we can see one of the accomplishments of doing all these things is we have hit value of our classification is greater than 0.9. It's 0.906 for eval, right? Greater than even the 0.899 that we hit before. And if we want to look at the plot, now remember that we are capturing two values in our rec, both the learning rate and the momentum. And this is what it looks like. It's learning rate starts low, goes high, turns low again. Momentum starts high, goes low, goes high again. Okay, so that essentially completes the lecture 17 for today. And we just have one more lecture on ResNets. And after that, all the subsequent lectures are how we use the infrastructure we have set up in order to understand much more about stable diffusion. So after next Saturday will still be ResNets and how that works, but we'll kind of be focusing, if you will, on stable diffusion. The one other thing I wanted to point out, because we spent a significant amount of time showing this, so I'll stop sharing the net and let me spend a few minutes on this that we have left. Let me know when you can see my screen, and you should see a spreadsheet. Do you?
Yeah, we can see it.
Okay, so this is another spreadsheet I would encourage each of you to play with quite a bit because it's very interesting and very, very visual. If you're a visual learner, this is really helpful in terms of understanding what a basic optimizer does, what momentum is, what RMS prop is, what Adam is, and things like that. So essentially what he's doing is he has the data, which, okay, so what he has is an AX plus B, where the B, the intercept is 30 and A is 2. And this is all the data points that he just provides as X and Y's. Eventually, we want our learner to learn B to be 30 and A to be 2. That's the answer we are seeking. Okay, so AX plus B, where A is 2 and B is 30. That's what we're after. Now, the simple thing that we want to do with the basic is to, and what he has done here is, let me see whether all this is set up, but you can play with each of these. So basic, momentum, RMS prop, Adam, and then an annealed version of Adam. So here what he does is he starts off with X and Y. He calculates or assumes an intercept and a slope. he does the y-pred using the intercept and the slope, calculates the error as a mean square error, the error in B1, and then the estimated D by DB, the error in A, the estimated D by DA, and then based on this, calculates the new A and the new B, and then plugs it back into this equation. So the new A and the new B would be 1.12 goes here, the slope, which is the X plus BA is the slope, so it goes here, and the new B 1.01 is 1.0086, redoes the whole calculation and keeps doing this. And when we run, let's say we reset it, when we run it, basically what it has done is it runs it 5 times. If I were to run it again, it runs it 5 more times. If I were to run it again, it runs it 5 more times. So what he's trying to do is illustrate for, and he does that through macros and shoves the value back. He calculates at the end of the 5 runs to the top and keeps repeating it so that he tries to figure out whether how quickly we get to the desired values. Remember, the desired value of A is 2, and the desired value of B is 30. So you can see that B is still far away, is not so terrible. But this is just the basic with no momentum, no RMS prop, just standard stochastic gradient descent. If you go to momentum, you can apply and you can see as momentum increase, you run it, it runs it 5 times, right? And the momentum value is using is 0.9, by the way. And you can see whether this is approaching, and you can see how quickly A, even with 5 runs, has gone to 2.3. Run it again, 5, run it again, and if so you kind of can play with this and figure out how quickly you can converge. And you can see that in this case, B is increasing much faster than before. Right, now switch to RMS prop and run that, and you can see how quickly B is increasing when you do the RMS prop. Because remember, our goal is to get B to 30, and you can see how quickly it's increasing compared to our prior standard value, right? And then add-on, if you apply add-on, you see how quickly B has gone to 25. Now you get, of course, 1.7, but that's not very far from the 2 desired value that we are at. You see that? And you can do the calculation for each of the data points. When you do it for all of these, that's mini batch. I mean, in this case, we don't have batches because we just do it for the entire set of data. But it's a kind of handy tool to really understand the map and with a simple example. Okay, any questions?
No, but I have a general question. You know, the recordings, are they available on YouTube or is it listed somewhere?
I think a couple of, it's there in the pinned thing at the top. There's a pinned spreadsheet on Google Drive, or my Google Drive. I've shared it, which has the links to all the recordings.
On the Slack thread, is that right?
Yes.
It's also available on the YouTube. I checked.
Oh yes. What's the name of that channel?
It's there in the Slack channel. I posted.
Okay, great. Yeah, I missed the first few, so I wanted to review them.
Yeah,
but this was great.
It's mine too.
Only thing is we missed
the last record.
Yeah, I will put the channel name in the.
Okay, any additional questions? So hopefully you can use that. It should be available. If you look at the channel, I think Ange posted a link to the YouTube channel as well in the Slack channel.
And it's like, okay, thank you very much. No, this was great.
Okay, thanks everybody for joining. See you all next week.
Thank you.